Okay, welcome everybody. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good afternoon, everybody here. Welcome to our webinar. Today, once again, we have a guest from New Zealand, Prof. Andrew Charleston. So, in this opportunity, he will deliver third course related to earthquake. So still, there are many questions about the role of architect in order to face earthquake disaster. Many of us may be still thinking that civil engineer is the most persons, the most party behind what happened in earthquake disaster related to buildings failures. But actually, there are many things related to architects who has a responsibility to make our building stronger as well. Because in many cases, we found that there are many failures in non-structural element related to architectural element in many buildings. And these failures can be make fatality, can make us in dangers. So that's why we are lucky today once again because we have Prof. Andrew Charleston. He is one of top scholar dealing with this matter related to earthquake in architecture. So please welcome Prof. Andrew Charleston here with us right now from New Zealand directly. So I think the time is yours, Prof. Andrew, please.
Okay, thank you very much for your kind welcome and your introduction. So good afternoon, everybody. Welcome again to this presentation where, as has been mentioned, it's the third presentation. In my first lecture, I talked about the vertical structure we need to provide in buildings to resist earthquake. And typical vertical structures will be moment frames or shear walls or even braced frames. And so my first lecture was talking about that sort of vertical structure. And then in the second lecture, I talked about horizontal structure and maybe some of the configuration problems that we have to overcome. And in this third lecture, I'm going to talk about non-structural elements. So please excuse me, and I'll just share my screen with you. And I just want to start the slideshow. Here we are. Okay, there we are. So is that clear? My first slide?
Yes, Prof, clear.
Okay, great. Okay, excellent. So first of all, you'll notice a rather strange feature of my title. And that is, I've put that question mark there because otherwise it would say non-structural elements and earthquakes, what architects need to know. And so today I'm going to be talking about non-structural elements. In other words, my talk today is about elements that you as the architects are primarily responsible for designing and specifying. But the reason for the question mark is that there are some non-structural elements that you design and detail, but actually, because of their strength, these elements act as structural members without you perhaps even realizing. And so that's the purpose of that question mark in the title. Now, I divide non-structural elements into two groups. The first group includes non-structural elements that are likely to damage the structure in an earthquake. And these are the elements that you design as architects, and you may not even tell the engineers about them. And there are two types of these non-structural elements, as you can see. There are infill walls and staircases. And so in the first group, there are just these two classes of non-structural elements. And these are elements that potentially can cause very serious damage to the structural members. And I'll explain shortly about that. So that's the first group. Now, the second group are all the other non-structural elements of the building. And these elements do not damage the main structure. But nonetheless, they need to be designed by you architects, and you have a responsibility, possibly with help from the engineer, in making sure that these elements don't kill people and are not especially dangerous, and also that they will be able to function after a small earthquake. That's perhaps as far as your responsibility goes as an architect. And so I'm going to start the presentation by talking about infill walls, because they have an ability to damage the primary structural elements, namely the columns of a building. And also, they are a problem because of the ease with which they can change the structural performance of the building, especially by creating or causing torsion. They can cause buildings to twist, and that can lead to, well, collapse of a building. And finally, the challenge that they pose is that they're usually quite heavy elements, these infill walls. And so if there's a chance of them falling inside the building or outside the building, then it's very likely they're going to cause very serious injuries to the occupants of the building and pedestrians who might be walking alongside the building. And so, you know, these are the main challenges that infill walls provide. Just before I go to the next slide, I just want to mention to you, I'm just going to make sure you can see my mouse. Can you see my mouse now? Is my mouse visible?
Yes. Yes.
Oh, Excellent. I just want to say, first of all, that my talk tonight is about infill walls. In other words, I'm assuming that, for example, there's a reinforced or steel concrete frame building. So the structure has been built, and then infill walls are then placed inside the structural skeleton. And so the walls are placed after the columns and beams have been cast. And so this type of construction is very different from confined masonry construction, where the columns are cast after the masonry walls are in position. And so this is what I mean by infill walls. And so as I proceed in my lecture, please do ask questions, because there should be plenty of time towards the end of the presentation for me to answer any questions you have. So please think of questions as I go along. Now, I just want to start my talk about infills by sharing with you a very recent personal experience I've had. I visited Albania in December last year, so what, about 6 months ago. And just 1 week before I arrived, Albania was hit by a moderate earthquake. It wasn't a large earthquake, it was like a moderate earthquake. And this, and near the capital city where I was staying, there was another city called Durrës that was quite close to the epicenter. And a few days after my arrival, I visited Durrës, and these are some of the photographs I took. And I was just shocked at the amount of damage to infill walls. And so this damage is still very fresh in my memory, and it makes me like very passionate about sharing my knowledge of infill walls with you. Because, I mean, look at this building here on the left after the earthquake. Like these walls, I mean, they just fell completely outside the building onto the pavement. And here's somebody's kitchen. Here's somebody's bedroom. And you can see some remaining elements of the infills. But you know, most of these walls are totally gone. And inside the building, there was huge damage to partition walls made of brickwork and blockwork as well. And many internal partition walls collapsed, you know, and killing people, unfortunately. And everywhere in Durrës, there were just tens and tens or hundreds of these buildings that lost their infill walls. Look at this one. Some of the infills totally fallen out, and a lot of infills badly damaged. And if the earthquake had continued a bit longer, well then most of these walls would have fallen out. And here on the right is another building that I walked past on the street. I mean, we just walked around the streets taking photographs. And occasionally we met very sad occupants of these buildings because they weren't allowed back inside due to the danger. But I mean, look at this building on the right here. You know, these infill walls pretty much totally fallen out and are lying on the pavements. And then finally, just two final examples to show you. Here's another building. I mean, imagine living in these apartments. And you'll see that all the other infills have got big cracks in them. See, there's a lot of cracking and damage. And as I say, like this infill is cracked on this and around here and down there. I mean, it's almost on the verge of falling out. So many of them are. And then the final example is a building that we actually went into. Many of these infills have fallen out, and you can see directly into the rooms. And this was one of the bedrooms that we went into. And I mean, just imagine how terrifying it would be, you know, to be lying in your bed and have big chunks of infill falling around you. And so, you know, all these infills, they were specified by architects because the engineers generally neglect the presence of infills. And we might talk more about that later. But anyway, it's your responsibility as an architect, you know, to choose the materials of these walls and to specify them and to show them on your drawings. Not only infills, but also partition walls, because they are equally as problematic. So, you know, you can see how I had this first-hand experience just 6 months ago. And so, as I say, I'm feeling quite sort of passionate about the problem that infill walls cause. Now, because of this infill damage, people weren't able to occupy their apartments. And so they will be without their homes for months and months and months until repairs are done. And these repairs are going to take quite a long time. I'd just like to say a couple of things before I leave Albania, and that is that one of the good features, if we could call it that, about this earthquake was that in this particular city, most of the infills were made from hollow clay blocks or bricks. And so they are somewhat, or maybe quite a lot weaker than solid masonry units. And because the infill material was weaker than, say, what you might use in Indonesia, it meant that there weren't many examples of the infills damaging the main structure. The second thing I'd like to mention is that in the Albanian code, there is a requirement that when you're designing an infill wall, you're meant to construct a horizontal reinforced concrete beam at mid-height to stop the infill falling out of the building. Now, nobody was doing that. You know, people were disregarding this requirement of the code. And an architect told me, an Albanian architect, he said, look, it's in the code. We're meant to provide a horizontal beam to stop these infills from falling. But nothing was provided. And the consequences were quite disastrous, really. So that's my fresh personal experience of infill damage. And so now I want to explain to you what the problem is really. And so we start the explanation by imagining a bare concrete frame in an earthquake. We could imagine the building has not yet been occupied. The structure is just nude. There are no architectural elements yet, just the structural framing and the floors. That's all. And so as the ground shakes in an earthquake, the frame sways sideways like this. The columns bend, the beams bend like that. And this is the shape that a frame takes when it is subject to earthquake forces. Every frame behaves like this. The columns bend and the beams bend, and the frame moves sideways. And as the frame moves sideways, this diagonal dimension, it increases. Okay, this diagonal dimension increases, whereas this other diagonal dimension is reduced because of the horizontal sway at the first story. And every frame building, you know, is quite flexible really. I mean, in a moderate earthquake, we would expect that this movement here would be about 5 centimeters, something like that, you know, for a typical frame building in a moderate earthquake, maybe 2 to 5 centimeters. Now we come to the scenario where we have an infill. This is the infill. And so during the earthquake, the building starts to sway sideways, but the infill prevents that movement to a large degree. And the reason is because most infills are very stiff and they're quite strong, especially if they are made from solid masonry units and then plastered. They're very stiff and strong. And so as the building starts to move over and causes this diagonal to shorten, this diagonal piece of masonry, it becomes in compression. We say we form a compression strut. And this, the forces here could be very large indeed. And if we are using solid masonry units, what happens is that the compression presses up against the top of the column and it breaks the top of the column here. It breaks it. It breaks all the concrete and the steel. So this is the main problem. So once again, as the building sways and this diagonal gets shorter, we get this compression strut that damages the column. Now, at the same time as we get the compression strut forming, we get this diagonal, the opposite diagonal, gets longer And as this diagonal gets longer, it creates a diagonal crack like that. And so simultaneously, we get compression along here, and next door to it, we get one or more diagonal cracks. And so when the earthquake reverses direction, we end up with diagonal cracks going this way as well. And there'll be a compression strut in this direction. And so normally after an earthquake, when you look at infill walls, you will always find these diagonal cracks. I mean, there will also be cracks around the interface of the columns and the infill too. You know, normally there'll be cracking here because the mortar breaks due to the movement. And so once these cracks have occurred, the infill is very unstable and is likely to fall, likely to collapse. So this is the explanation for why infills get cracked, how they form compression struts, and how those struts cause damage at the tops of the column and sometimes at the bottom of the column as well. It can be damaged as well. So maybe you are starting to get one or two questions from my explanation. So please just type them in, and we'll come to them as we get to the end of the presentation.
Yes, Prof. Andrew, there is one question here from Pak Buti. Would you please explain again about infill wall? Is it mean if wall installed after concrete structure casted is not infill wall or the other one?
Yeah, thank you. Yes, these infill walls are constructed after the structure. So the columns are finished, the beams are finished, and then the mason comes and lays the brick wall. And so usually the brick wall is not anchored strongly to the columns or the beams. So that's the infill I'm talking about. And what I said earlier was I'm not talking about confined masonry construction, where you build your masonry walls and then you cast your tie columns and your tie beams. Because we know that confined masonry, which you use a lot for housing in Indonesia, can be very effective at resisting earthquake, but not infill walls. They are problems.
So what kind of infill walls most create a problem, Prof? Is it only brick wall or another infill wall as well?
It's only infills that are stiff and strong, like masonry, brick, or concrete blocks in mortar. And so they are the only walls that, well, they brick and concrete masonry, yeah, they are the primary infills that are causing these problems. And
So,
as I will explain at the end of the lecture.
So you mean that the heavy wall only create problem, while the light walls, it's safe for the high-rise building. Is it like that?
Correct. It's as simple as that.
Okay, thank you, Prof. Andrew. Please continue.
Yeah, so now I want to just elaborate a little on how infills can cause problems to the structure. I've already explained how they can cause damage to the tops of the columns and the bottoms of columns because of the compression strut. But there's almost a more dangerous way they can affect structure by creating soft stories. So let me explain. Here is a very simple building, 1 bay wide. And at the ground floor, there are no infills. This is just open, maybe for parking. And then above, we've got infills here. And the masonry infills, as I said before, are strong and very stiff. And so when we get earthquake loads occurring on this frame, this story and this story, they are very stiff and strong compared to the ground floor, which only has the 2 columns. And so if this building gets damaged, it will be at this soft story. And unfortunately, when we have damage in a soft story, we might get column shear failure like that, which will lead to the building collapsing. Or we might get a lot of damage in what we call the plastic hinges at the tops and the bottoms of the columns. And that can lead to very, very serious structural damage. And it's all because of the great strength above. And so like this story, it becomes like the weak link in the chain. And this is where the building will break. And here's an example of a soft story building, actually in India. See how the ground floor is open? But above, you've got masonry infills, making the upper floors very stiff and strong. And so in an earthquake, these columns, you know, will get severely damaged and the building will probably collapse. I'm going to show you some examples of buildings with soft stories caused by the infills. And here's a building also in India. See how the bottom story has collapsed because it probably was open. But look at these strong infill walls. They haven't even cracked because they're so stiff and strong. And so over here, you can see some diagonal cracks in the infills, but actually there's been quite a lot of damage to the infills, but this particular part of the building is still standing. Here's another building where the infills are quite badly damaged in the stories, in most stories. But see, this story has collapsed because probably there weren't any infill walls in it. Maybe in this story, the architect had just used light cladding. But for the other stories, strong infills have been used, and that has made this story to be very weak, and the whole story has just totally collapsed. Usually, it is the ground floor story that is the soft story. That happens in about 90% of the cases. So this is a bit unusual to have it mid-height, but it happens. And so let's look at the damage to the tops and bottoms of columns. Here's a building that has been through a large earthquake. You can see the damage to the infills. Some have fallen. But if we look carefully, we can see the way, for example, this column has been damaged, caused by the compression strut up here. You can also see diagonal cracks in some of the other remaining infill walls. Here's another building where the columns have been damaged by the infills. See how the top of this column has broken. The concrete has been lost and the bars are buckling. Here, the bottom of this column has gone and the top of this column has gone. And here you can see like a diagonal crack has passed through these two panels. You can see extensive damage to these infills because the frame is pretty flexible, and therefore the stiffness of the infills means that they will suffer a lot of damage. Here's an infill wall here that has caused damage to the top of this column. And so the whole floor slab has moved down and it's pushed the infill wall out to the side. And this is actually a supermarket building in Indonesia that I visited many years ago. It's near Lake Toba, actually, in Sumatra. And first of all, you can see some infill walls have collapsed and are sort of lying on the floor. But notice the tops of all these columns, badly damaged because of the compression strut in the infill before the infill fell over. And this damage occurs everywhere in the world during an earthquake where these strong infill walls are used. I mean, these infill walls look as if they've been made from concrete blocks, don't they? I can't see any bricks actually. So this would be concrete block plastered to create the infills. And you can also see like there's no connection between the columns and the beams and the infills. There are no bars sticking out, nothing to stop the infill falling once it gets a lot of cracks. And the final way infills can affect the structure is by creating torsion or making a building twist. Let's look at the plan of this building. It's a symmetrical frame building, columns, and there'll be beams maybe everywhere, very symmetrical. And so the center of resistance is the same as the center of mass. So during an earthquake, the earthquake force will like act through the center of resistance and the center of mass. Now let's imagine that the architect decides to put in some infill walls on this line. These infills are very stiff and strong because they're made of masonry, we assume. And that has the effect of moving the center of resistance from the middle of the plan right over to here. Because this area now is so strong compared to the rest of the frames that are relatively flexible. And so during an earthquake, the earthquake force acts at the center of mass, which is more or less the center of the floor plan, because the floor is very heavy in a building. But the resistance from the earthquake occurs through the center of resistance, which is close to the very stiff infills. And so this forms what we call a couple. And so this forces the building to twist like that. And so as you can see, the twist is shown by the dotted line. And the problem with torsion is that when a building twists like that, some of the columns that are far away from the center of resistance, they have to move sideways a large amount. And when they move sideways so much, they get so badly damaged that they can't stand the weight of the building any longer. And that floor will probably collapse. That's the problem of torsion. And so
Prof. Andrew, I'm sorry. COR and COM, what is the meaning? There is a question about that.
yeah, COM stands for the center of mass. Like that's where the center of gravity is for the weight of the whole of that building. The center of resistance is the COR. And that is where like the center of all the earthquake forces are resisted by the building. And because of the infills, the center of resistance is close to the infills. And so this slide illustrates the potential danger if infills are not symmetrical. You know, they can cause the building to twist. They can cause the columns, some columns, to move sideways a large amount and force them to break. Maybe I'll just pause and see if there are any questions from the participants at this point.
Yes, professors. There is a question about what from Nadia. What the alternative of infill wall instead of brick walls?
Okay, well, I'll have to ask that person to be patient because I'm coming to that soon.
Okay.
Please just be a little bit more patient with me.
Yes.
And I will answer your question.
Okay, Prof. About the soft story, it's common happen actually in Indonesia from last many earthquake happen in Indonesia. But unfortunately, many architects prefer to open the ground floor because of economical reason. They can open store, they can use as public space, they can use as a garage for cars and so on. So what do you think about that?
Well, I've got quite a few ideas that I'm going to share with you in a few more slides.
Okay.
So
Okay.
you've got to be patient too, I'm sorry.
Okay. So please continue then.
Okay. Well, here we are. Now I'm going to talk about the solutions. Okay.
Okay.
I've been very negative so far. I've been just telling you about the problems. But my purpose has been so that you understand what the problems are. So now I've outlined the problems. I'm talking about the solutions, and they're going to be a number of solutions. And this slide really gives you the philosophy of the solutions. We have to separate the infills from the frames. This is one of the key solutions. So let me explain further. Here is an example of separation. We have our frame and we allow it to sway, but we want an infill. What we have to do, if we want to use a strong infill like masonry, we must design separation gaps. Physical separation gaps. Maybe someone can switch off their microphone, please.
Yes, sorry, Prof. Okay. Now.
And so the idea is that we create these gaps between the edge of the infill and the columns so that when the frame moves in an earthquake, the frame will not hit the infill. And so the infill will not cause a diagonal strut to affect the structure. And so in practice, in some countries, it looks like this. Here's the concrete frame. Here is the infill. Here are the gaps, physical gaps, maybe 2 centimeters wide, maybe wider. And then to stop the infill from falling from the building, we must have practical columns. You call them column practice, I think. Practical columns, and they will stop the infill from falling at right angles to its length. And the tops of the columns, they have quite a flexible connection to the beam because there is movement along this line. There's about up to 4 or 5 centimeters of movement along this line. And so the steel bars have got a bend. And they'll get a bit damaged, but that doesn't matter. They will protect the infill from falling. and the gap, that will stop the infill from damaging the structure. Now, the gap is a problem for architects because the architect has to do detailing to stop the rain, the wind, fire, and so on. And so if you have gaps like this, it's a challenge for you to do the detailing. But there are many examples of buildings using this approach. And I'm sure you'll have questions for me about this. Here's an example of an infill. Well, this actually is a partition wall in New Zealand. This is a frame. This is the floor above. This is the wall. And can you see this steel hardware here? And so it's like this. If I can explain, my hand here is like the wall, and this is the steel plate bolted to the floor above. And so in an earthquake, the floor above can move without affecting the wall. But the wall can't fall because it's restrained by the steel plate. And so the separation is achieved by allowing that steel plate to move like in a groove, but then to prevent the wall from falling by the strength of the concrete blocks, like that. I'll just go back. And so that, so this is one solution to separate. And so as the architect, you have to ask your structural engineer what gap you need, because the engineer has to do careful calculations to work out how much your building will move sideways during an earthquake. And your structural engineer might say to you, well, look, you need to have a 5 centimeter gap here. Now, if you might say, look, that's too wide. I don't want to have gaps 5 centimeters wide. And then the engineer could say to you, well, okay, if you don't want to have wide gaps, I can make the frame stiffer so that it won't move so much. And so then the engineer can make the columns and the beams a bit larger, and maybe the gap only has to be 2 centimeters. And so you as the architect, you can sort of have negotiation and discussion with your engineer. And say you say to your engineer, look, I don't want to have any gaps. Well, then the engineer would have to say to you, the only way that is possible is for me to design the building with very, very stiff shear walls, which means that the movement will be very little, and therefore you don't need gaps. But now your planning will be affected, won't it? Because now you will require very strong shear walls in both directions in your plan. But the good news is that there are other solutions. And we've already discussed one solution. Use lightweight cladding. So if you're using cladding of, say, plywood or can you tell me what sort of lightweight claddings might you use in Indonesia these days? You might use fiber cement sheets, mightn't you? Fiber cement cladding. Well, you know, that is very weak and light. No problem. It won't damage the structure. It won't cause soft stories. The second option is to use, say, like precast panels as infills, or maybe on the outside of your structure, but you design the connections of these panels to allow movement. And so it's a bit like an analogy of a snake or a fish. You know, like a fish has very stiff scales, but the scales are only attached like at a couple of points. So the fish is very flexible, but then the scales don't get broken. And the scales don't stop the fish from being flexible, or the snake. I'll show you an example in a minute. And the final option is, as I've said, if you want to avoid damage to infills, then you have to create a very stiff structure with shear walls, with structural walls. Then your structure is not going to move much in an earthquake, and your infills won't get damaged too badly. So one of the take-home messages for you is that if you're proposing to use stiff and strong infills, you must discuss it with your structural engineer early in the design process. That is really important. And I must say that some structural engineers are not very knowledgeable about infill walls. And so it is a warning really to try and go to a structural engineer who's got experience and understands the problems and the solutions to infill walls. So I'll just pause and see if there are any questions at this stage.
Yes, Prof. There are some questions, I think, from Ibu Ana Ramdhani Sari. She's asking about enlarging the dimension of the column, maybe can help to mitigate the risk of this happen, to prevent this thing happen when earthquake comes. Enlarging the size of the, it means that make structural system more stiff, isn't it?
That's
so,
right.
Yeah, it was one alternative of the solutions, isn't it?
Yeah, it's not really a solution, because if you make a frame structure stiffer, all it means is that you are reducing the amount of movement. Like maybe before you made the structure stiffer, maybe the movement between each story was 5 centimeters. Now that you've made the structure stiffer, maybe the movement is only, you need a 2 centimeter gap. So even though you have made your frame stiffer, you probably still need a gap. Otherwise, you'll get those compression struts causing damage to your structure, and you will cause soft stories and other problems.
So this is also a question from Pak Wahyu Buana Putra. So how many centimeters gaps between the walls and the column? So shall we discuss this thing with our engineers, of course, isn't it, Prof?
Yeah, that's right. Every building is different because it depends on the stiffness of the structure the engineer has designed with you. I mean, if you've got a very, very flexible structure, your gap, it could be as much as, say, 8 centimeters. But if your engineer and you agree on a stiffer structure, the gap might only be 2 centimeters. So as I say, this is something for you to discuss with your engineer quite early in the project.
Okay, and more stiff the buildings, it will be more expensive for the structural system.
Yeah, it will, won't it? Exactly. But look, remember that the cost of the structure of a building is about 25% of the total building cost. And probably, you know, the cost of all the infills and partitions in your building, I mean, they are probably about the same cost. And so it can be like a good investment to protect your infills as well. And by having these separation gaps, you'll do that. But if you are concerned about your infills, then I think, you know, I recommend you try and use the first 2 solutions. And so you don't use heavy masonry infills in your building. You try and find alternative means of cladding.
Okay, Prof. I think that's the best solution for the lightweight building, such as tower, because, you know, as a high-rise buildings, more weight will have a possibility to easily sway if we use the heavy structural systems such as concrete, reinforced concrete, and bricks infill walls, isn't it?
Yeah, that's right. Yeah. So that's right. So if you don't use brick infills and brick partitions, you're making your building quite a lot lighter, and therefore it will attract less earthquake load, and therefore your structure can be smaller and cheaper.
Yes, yes. So lightweight structures will be cheaper.
Absolutely.
If I'm not wrong.
Yeah, and safer.
And safer. But we have to use more steel rather than reinforced concrete in that case.
No, you can keep to your reinforced concrete frames if they're properly designed. They're okay.
What about the sway or the, because it's not stiff if we're using small system, small column and beam systems.
That's right. So if you use a frame system, it's going to sway, but the Indonesian code gives the maximum limit to sway. And so the engineer always has to make sure that the building won't sway more than the code allows. But engineers are allowed to design quite flexible buildings. And that's what I said. Typically, an engineer is allowed to design a building that will sway about 8 centimeters per floor. That's like what your code allows. Okay, so
Okay.
and that will mean the engineer will give you the smallest possible dimensions of your columns and beams. But it will mean that in an earthquake, each floor will sway up to about 8 centimeters.
8 centimeter. It's 8 centimeter in what height?
Per story.
3-story.
No, in each story.
In each story.
Yeah.
Okay. So from Purita, there is another questions. For example, for existing buildings, how to give more stiff to the structural systems for the existing buildings?
Well, each building has to be evaluated separately. But like, say you have a building with an open ground floor with stiff infills above. Well, one way to improve that building is to create separation gaps between the infill and the columns and beams. And that might prevent a soft story occurring. There are actually many different ways we might retrofit a building. And as I say, each building is different and has to be carefully considered, on its own merits. I mean, if you had a building, like, let me go back a few slides.
Okay, please.
Well, say you had a building like this, and you came to me and said, look, I'm worried about my building. And I would say to you, yes, you should be worried because you're going to have a soft story here. And so, look, I would say to you, the best thing you could do would be to remove these infills and replace them with lightweight cladding. Then your problem goes away. So, yeah, heavy, stiff and strong infills, are certainly a problem. Except that if you had a building where your infills went right down to the ground, then the infills might be helping your building. In some instances, your infills can help, but the infills must start at the foundation and go to the roof, and they must be symmetrical in plan. Then it's possible for infills to be okay. But we might have to add some practical columns to stop the infills falling. So you might have to add some practical columns just to stop your infills falling in or out of the building in an earthquake. That's all you might have to do. And that might make your building to be, you know, safe enough. Are there any other questions at this stage?
Okay, please continue, Professor.
Okay. I want to talk briefly about partial height infills because they are very common. Like here's a frame. This would be glazing, and so the infill only comes to this height. So how do we separate that? Well, what we need practical columns to support the infill for what we called face loading, to help stop the infill falling. Here are the gaps to allow for the movement. Here are the gaps calculated by the structural engineer. And then to make sure that the infill doesn't fall when there's shaking, like this is a plan. Like here's the wall, here's the column, this is the gap, and see we need like 2 steel brackets in the corners, and that will prevent the infill falling into or out of the building. And I mean, this is a very crude detail, but it just shows you the principle. So the frame can move this is the steel bracket, here's the wall, and the wall can move, sorry, the column will move like this, but there'll be no structural forces forming in the infill because of the separation. And the infill can't fall because it's restrained by the 2 steel brackets. I mean, this is what we would design in New Zealand or in California, Japan, you know, many other countries, something like this, for partial height infills. I mean, if possible, we would try and make these infills lightweight. But if that's not possible, then we'd do something like this. Or we would use some type of precast panel cladding. And I'll discuss that in a minute, I think. I don't know, no, maybe I'm not going to discuss it. Well, I think I'm leaving infills now. So just before I leave infills, shall I see if there are any questions?
There is no question up to now, Prof. So, yeah, you might continue or?
Yep, I'll continue.
Okay.
So you'll remember that there are only two types of non-structural elements that damage the structure. The main element is infill walls, and the second element are staircases. They can cause serious structural damage. But fortunately, the solution is so simple. So what's the problem? Well, just let's imagine a very simple scenario. Here's a building, and here are stairs going up each story like that. Now, in an earthquake, these stairs can function like a diagonal strut. And so in many buildings, when there's an earthquake force occurring, pushing the building sideways, these stairs go into compression. And they can go into tension. And of course, stairs aren't designed to be structural. They're sort of non-structural elements. But if we're not careful, the stairs think they're structure, and they accept very strong compression forces or tension forces. And that causes a lot of damage to the stairs, and it damages the structure. Also, if we have a symmetrical building and we introduce some stairs here, those stairs can be like diagonal struts. And once again, we move the center of resistance over to the stairs, and we cause torsion. And we get severe damage to our building, just like infill walls do. Here are a couple of buildings with severe damage to the stairs, here and here. This stair has tried to act as a structural element. The solution is so simple. We imagine we put the bottom of the stair on a roller. And so that during an earthquake, when the floor above moves, the stair just slides on the slab beneath. A simple sliding joint is all that we need as a solution. It's so simple. And so what we do is we have just maybe a plastic sheet here. So, and there's no bond between the stair and the slab. Just sliding can occur. And then if we do that, the stairs just slide on the slabs and they don't become structural members. They don't cause damage and they are not damaged. It's a perfect solution. Incredibly simple. In fact, in Wellington a few years ago, an architect designed this sliding joint, and he actually used little wheels like this, you know, to articulate, to express the movement. And I'm sorry, I haven't got an image to show you, but it was a very nice little detail, showing the way that the movement, the rollers were meant to slide during an earthquake. It was very nice detailing. Okay, well, that's all I'm going to say about stairs. I'll just see if there are any questions about stairs.
Yes, there is one question from Pak Sibuya Wibawa. How about RAM, which used for vehicle circulation? Is the solution will be same for the RAM as well?
Yeah, the same solution for a ramp. Yeah, that's right. If you've got like a vehicle ramp, exactly the same. We would make it slide either at the bottom or the top. It doesn't matter. As long as the ramp can't form like a diagonal strut. Yeah, that's such a good question. And that person has got a very good understanding of how to solve it. Have a sliding joint either at the top or the bottom. Really simple.
And the materials for this aspiration is just only the sheet of fiber, isn't it?
Yeah, I mean, I've shown there a plastic sheet. Anything that allows, you don't actually need anything. Like it just could be concrete sliding on concrete.
As long as spared from others.
Yeah, as long as there's no bond.
Yeah, it was from Ibu Rosmiati Arifin and from Pak Jafar as well. What about the symmetric way, Prof. Andrew? Sometimes in the buildings, we put the staircase just in symmetrical way. So it will be have a problem with this way, or still we have to use this aspiration on the bottom of the staircase?
Yeah, you should always use a separation because the building is going to move, it's flexible. And if you don't separate, or sorry, if you have two stairs that are symmetrical,
Yes.
okay, there's no torsion. So that's good. That's good, no torsion. But you will still get the diagonal struts forming. And that means that the stairs will get damaged or they will damage your structure. So as a rule of thumb, yeah, every stair needs separation. And even if you have like steel stairs here, what you would do is you'd have a bolt in a hole so movement can occur. You know, always allow for that movement to occur.
So including staircase in the core, for example, we also use this technique as well from Nadia
Yeah,
Dewi.
that's right. Yeah, you should do it in the core as well. You don't need to do it if your building has got very stiff shear walls, because then there's going to be very little movement. And so you don't need to separate. But for the vast majority of buildings, we need to have these sliding joints. But as I say, the beauty is that they're so cheap and they're so easy to make, you know. There's really no problem with them. We just have to detail them and specify them.
Is there any instability issue if we spirit this from main structures or professors on the staircase itself?
No, none. All that happens is that the bending moment diagram will change a bit here, because like the engineer might assume that this end is fixed and this end is fixed. and therefore maybe the stair can be a little bit shallow. But if we have a pin sliding joint here, it does mean that the stair has to be a little bit deeper here, just the fraction.
Okay, then. So from Pak Budi, so far the stair, is it better to put the supporting element not at the end of, sorry. From Pak Budi, is it better to put the supporting element not at the end of the stair due to at the end of the stair need to be separated? For example, we put supporting column in the middle of stair. It's needed to put supporting column in the middle of the stairs.
No.
Not needed.
No, it's not. Like, I mean, you could have a stair like this made out of, you know, steel or concrete, spanning between here and here. And as I said, here you'd have your sliding joint. If you wanted to, you could put a column here, but you would still need to have the sliding joint here. Otherwise, you're still forming this diagonal strut, aren't you? Even if you have a column just supporting your stair. So yeah, you can have a column here if you want to, but you still need this sliding joint. Otherwise, we get this problem of the compression or tension in our stair that will damage it, it'll collapse it, maybe.
Okay, Prof. From Pak Jafar, what about the other sides on the upper part?
You mean like here?
Yes. Is it the same things?
No, here you will cast your stair into your beam and slab at this level. So at this level, your stair will be strongly cast into the concrete structure. Because like half the weight of your stair has to be resisted up here. And the other half of the weight of your stair can be just resting on the slab. So yes, we must definitely have a strong connection at the top of the stair.
Mm-hmm. What about the other way around, Prof. Andrew? Making roll on the upper part and fix on the bottoms.
In theory, you can do that. In theory, that's fine, because you are achieving the horizontal separation. So in theory, it's perfect, but in practice, it's more difficult to detail.
Mm-hmm.
The detailing is a lot more difficult.
Okay, practical reasons.
Yeah, let me just.
Was from Pak Yeri Suyadi.
Yeah, let me do a drawing to illustrate what I mean. This is on the back of an envelope, but it could be like this.
Yeah, this is also from Ibu Eva Suryani as well about detailing on the roller joints.
Can you see my wonderful sketch here?
Yes.
You see, that's the detail where the stair can slide at the top. there's a gap between the stair and the column, and the stair is supported by that little cantilever for gravity loads, and there's a sliding joint there caused by, maybe made by just 2 sheets of plastic. But that detail is rather it's rather complicated compared to having a sliding joint at the bottom.
Yes. Okay. That's all up to now. The questions, Prof. Andrew, please continue.
Okay. Now I'm going to talk about all the other non-structural elements that we have in our buildings, that we as architects have to think about. And I'm going to start with cladding. So, often we use infills as cladding, don't we? But in many countries, like here's an example of, this building was in Australia actually after an earthquake, and it was a brick building with a brick veneer. See, like this is the load-bearing masonry, and this was the veneer for weatherproofing. And during the earthquake shaking, the cladding just fell off. And so if we want to have brick cladding, then we need to provide little posts that are attached to the structure at the top and the bottom. And then we need like ties. The best are stainless steel ties so they don't corrode. So that in the shaking, the veneer is supported by these vertical timber or steel posts or studs. But for most buildings these days, where we want heavier panels as cladding, we might use precast concrete panels, and we won't use them as infills. We will attach them outside the frame. And so like here are some concrete panels that are being attached to the outside of this concrete frame. I mean, these panels have glazing, so they've got quite big holes in them. But if you look carefully, you can see 4 pieces of steel where the panels bolt to the main structure. And so the philosophy is like this. We can hang panels from their tops. So at the top of the panel, we have steel fixings that are designed to support the whole weight of the panel. And then at the bottom of the panel, we allow for the movement. And so see how these holes are elongated. I don't know if you're familiar with that word, elongated. But that means that when the building moves further at the top, the panel can just move to and fro without breaking the bolts. And so there's movement ability there. The other option is that we support these cladding panels at their base, like on this line. And maybe there are 2 strong steel connections. And then at the top of the panel, it's connected with elongated holes. so that when the frame sways sideways to and fro, the bolt moves in this hole and the bolts don't get snapped off. Now see this elongated hole here? That's what's provided in this building. See these elongated brackets? That's to allow the frame to sway sideways to and fro, and the cladding panels won't get damaged. This is like the analogy of the scales on a snake. You know, the body is flexible, but the scales are rigid. Like this panel is rigid. And therefore we need this flexible movement ability, in this case at the top of the panel. And of course, this is really good because now there's no infill. There's nothing to damage the structure. You know, the stiff panel is not in the plane of the columns and beams. It's outside, and that's perfect. And it's easy for the architect to detail this. It's easy to detail it for weatherproofing, you know, for wind and so on. And so, you know, most buildings in the US and in New Zealand and Japan, you know, would have exterior cladding like this. Or it could be like curtain wall, something like a curtain wall. It's the same principle. So that's one idea for cladding. The other idea for cladding is to make the cladding out of lightweight materials. Like here's a vertical section. This is say cement fiber board cladding. This is the wall structure behind it. It could be steel or timber studs. And here is a sliding connection that allows sliding so that in an earthquake, the panel won't get damaged. And if we look in plan, we also have the same idea. We have the sheet and gaps and so on. Here's a column. Here's the sheet cladding. Maybe some sealant, maybe a plastic cover. And so we have this very flexible, you know, skin on our building that can accommodate the earthquake movements of the structure. Very common in earthquake zones. Any questions about cladding?
Not yet, Prof.
Okay, let's move on to glazing.
Yes, one question here. Prof. Andrew, what's dimension of elongations, brackets, and how deep embedded to columns?
Yeah, that's a great question. Well, once again, the length of that elongation is given to us by the civil engineer. The engineer has to calculate how much the building is going to move in each story. And the elongation will be, you know, it depends on the flexibility of the structure. If you've got a very flexible structure, that elongation might have to be up to 15 centimeters. If your structure is quite stiff, the elongation might be 4 centimeters.
So it will be the same principle with the gap of the infill walls.
Exactly, exactly.
Okay. It was from Bu Elfa Suryani. Thank you, Prof.
Thank you. Yeah, it's a really good question. And so we take that same principle into the glazing. You know, in a building, when the building moves sideways due to flexibility, the windows are in danger because once again, this diagonal gets shorter. And so the principle is that whenever we put glazing in, we must have a clearance gap, a gap between the edge of the glass and the mullions or the structure. A little physical gap between glass and the frame. And so once again, we need to ask the engineer, especially for a high-rise building, you know, what gap do I need, please? Because otherwise, if there's no gap, the building sways, all the windows get broken, and the glass is very dangerous because it cuts people. And so this is the philosophy. We always have this clearance required around the edge of the glass. Oh, I'm sorry, I haven't got any details to show you today in my book. But I mean, if you look at the information about glazing in high-rise buildings, you will always see there is allowance for movement. The glass is never hard up against the frame. There's always a gap, a clearance gap. And so when you are designing your building, before you write the specification for your glazing, you just go to the engineer and say, engineer, how much gap do I need? You know, does it need to be 0.5 centimeter or 2 centimeters? And that the engineer has to do the calculation for you. And then you know that when the building sways to and fro, the glass is not going to shatter. It's separated. So we come back to the same principle, don't we? Separation. It's a very common principle for non-structural elements. Shall I move on?
Yes, please.
Parapets. Parapets at the roof of buildings are very dangerous because at the top of buildings is where the accelerations are worst. Because during an earthquake, a building resonates, and at the roof level, any parapets often fall off. And so what we have to do is to design simple steel brackets to prevent the parapet falling. Or we can provide like practical columns in the parapet also to stop that falling under the influence of the shaking. So they're quite simple to restrain. So for parapets, we must restrain them. What about partition walls? Well, if you can, you should always use lightweight partition walls because you are having a lighter building you can save costs in the foundations and in the structure, and you make your building a lot safer. And so, if possible, use light partitions, and sometimes we separate them. And so if you look at this detail at the top here, we've got the partition wall here, and we've got a little steel channel. So we can have movement without damaging the partition. And also the channel stops the partition from falling. So we come back to that same principle, don't we? We have movement in one direction, but restraint in the other. I mean, in many buildings, we won't worry about this channel, because if we're using lightweight partitions, they can absorb the earthquake movement, sometimes without much damage. And a lightweight partition will never cause damage to the structure. It's too weak, it's too flexible. So we don't need to worry about that. But if we're with a client who wants to protect the partitions from damage, this is one option. Something to have a sliding connection like that. Like, I mean, that might be a good investment, yeah, for a building where very high, very expensive finishes are being used. It could be quite a good investment. Okay, suspended ceilings. I could show you, if you go to the internet and search under Google for suspended ceiling damage, in every earthquake, hundreds of suspended ceilings fall, and they can injure people quite badly, or they cause havoc. And so the solution is that there are three solutions to suspended ceilings. Sorry, I'll go back. We can brace them. See the diagonal bracing? Here's the suspended ceiling, just hanging from wire ties, as usual. But usually we don't put in the bracing. And so during an earthquake, the suspended ceiling shakes around like a pendulum, and it crashes against the walls, and it causes so much damage. So this is what we usually recommend. We brace the suspended ceiling. It costs a little bit more money, but it means that the ceiling won't collapse in an earthquake. And there are two other methods there too. So if we brace the ceiling, it looks like this. Here's the suspended ceiling of the ceiling tiles. They are hung from wire supporting the ceiling runners, which would be aluminium probably, or it could be it could be steel. And then every now and then in plan, here's the bracing bolted to the floor slab above. And so in plan, if this is your ceiling, say every 5 meters, say, brace in this direction to withstand shaking in this direction, and then in the X direction, a brace here, a brace there, and a brace there. So it's quite simple, but we have to be very strong as architects to make sure that this bracing is done properly, because most contractors don't like doing it. Okay, so suspended ceilings we restrain them. We stop them shaking like a pendulum. And this bracing is really simple and okay, it maybe costs 10% more or something, but your client won't have all their ceilings dropping in an earthquake. No one will get injured from the ceiling.
Yes.
What about mechanical equipment and things like water tanks? Well, we have to restrain them. And so when these items are installed in the building, we've got to make sure that they are restrained. Otherwise, in an earthquake, they're going to slide or they're going to overturn. And I mean, the problem with water tanks is that if a water tank overturns, the water spills and it trickles through every floor of the building. And you've got to refurbish your whole building. Everything has to be ripped out because it got wet and things get rotten. And so, you know, it's really important to restrain your tanks or your mechanical equipment. Otherwise, you know, it'll get flung around, especially if it's at the top of the building where the accelerations are maximum. And so as the architect, you perhaps need a conversation with your mechanical engineers and check that all the items are bolted down, they're secure, they're restrained. They're not going to overturn or collapse. And even with, you know, piping should have simple diagonal bracing as well to restrain it from shaking. Otherwise, the pipes will break, you know, and the water will go everywhere. And it'll be incredibly costly for your client to have to repair. And so there we are. That's the end of my talk.
Yeah.
And so I thank you for your attention and just invite any final questions.
Okay, Prof. Andrew, it is very, very interesting. Thank you very much. I think your presentation helped us much because we are facing the earthquake almost every day. And what you just present to us from some of us, actually it's really new knowledge, because many times we neglect this, or we are not considering all these things to our designs. I believe in New Zealand there are many things to be considered, just like you present to us, but unfortunately in Indonesia we are not thinking too much about all these non-structural things deeply, like what you present to us. So that's why, if I'm not wrong, there are some keyword from your presentations, how to deal with the earthquake for, let's say, architectural elements or non-structural element. We have to use aspirations. The first bold underline that I got from you, aspiration is needed to our non-structural elements, such as walls, staircase, cladding, and parapet as well. But we also think about how to restrain from collapsing or from heat heating, the other elements such as mechanical equipments and parapet as well. So these separations, I think, is very important for our building elements. And also the second one is about like structures. Is it important to think about how to make our building as like as we can? And this like structure will less costly. And also the other one, we have to think about the stiff structure in other way. But stiff structures, of course, it will create heavy buildings. It will affect high costs. And that's why it less suggested to make this such building in our earthquake prone area. And I think the examples that you give to us actually give our new vision about how to deal with this to our buildings to face the earthquake. So I think it was very, very interesting to us. So this definitely will very useful to us to make our building safe. And of course, people inside. So I think that's all, but let's check the question if we got. Yeah, from Ibu Rita Laksmita Rahayu, just asking how to contact you. So maybe if you don't mind, I will give her your email address, yes. Prof. Andrew.
Sure, sure.
Okay, thank you.
I'll be pleased to answer her question.
Okay, and from Pak Andri Mailana, IAI, Peca Indonesia. It is good knowledge for me, so I can easy to discuss about my design concept to all my friends, structure engineers in BK, New Zealand. Oh, he has many friends from New Zealand as well.
Oh, that's nice to hear.
Yeah, so it's good idea, Pak Andri Mailana. And also from Ibu Nadia Dewi, thank you for the knowledge and the time for the discussion, Prof. Andrew. Yes. And
welcome.
Yes. From Pak Andrew as well. Nice to meet you, Prof. Andrew, and thank you. So that's all I think for now. And Prof. Andrew, once again, really thank you very much, very much to you that you give us your priceless times for these 3 webinar. So hopefully in the near future we can do more than this one, if you don't mind, of course.
No, I'm really open to that. I would enjoy that.
Okay, thank you very much, Prof. Andrew. So that's all for today. And okay. I will open anybody, all of you, to say something to Prof. Andrew Charleston if you wish. Please open your microphone.
Thank you, Prof.
Thank you, Prof. Andrew.
Thank you, Prof. Andrew.
You're very
Prof.
welcome.
Andrew.
Thank you all.
See you next time.
Okay, goodbye, everybody.
Thank you, Prof.
Bye.
Andrew.
Thank you, Prof.
Okay. Once again, thank you,
Thank
Prof.
you.
Andrew.
Thank you.
Thank you, Prof. Thank you.
Indonesia.
Okay.
Thank you.
Bye, everybody. Goodbye.
Has participated
I'm off to bed.
Webinar. Thank you for all of you. You have joined with us, and hopefully next time we meet you again. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, see you.
Yeah.